Hi, I am Hakam from the Computer Vision Group at the University of Bonn. Today I'm going to present our work on identifying spatio-temporal drivers of extreme events. In this work, we focus on agricultural drought as an example of the impacts of extreme events. But this could be any type of impacts. And we ask the question, which climate variables are associated with these impacts? The spatio-temporal relations between the impacts of extremes and their drivers in climate data are not fully understood, and there is a need of a machine learning model to identify such relations. As drivers of extremes, we consider anomalies in the land and atmospheric state variables. The task, however, is very challenging, since these drivers can occur at different time and location than the impacts. For the task, we propose a new approach that can jointly predict the impacts of extremes along with the drivers associated with these events. The input is a weekly mean and standard deviation for each input climate variable. We use here a multimodality to extract features from each input variable separately. In the next step, we use a quantization layer that takes the extracted features as input and predicts binary mask for each input variable at each time and location as drivers of extremes. In the last step, we take these identified drivers as input and predict the impacts of extreme events. Our model is trained in an end-to-end manner, using the joint objective function shown here. The first part of it is a binary cross entropy, where E hat is the ground truth data for the impacts of extreme events, reported for example from remote sensing. We use a multi-hit classifier to predict the impacts of extremes from each input variable separately. In addition, we use a multivariate prediction. S is just mask for the loss where to be applied. The second part of the objective function is related to quantization. The first part of it is a commitment loss. The second term is used to encourage the network to have a confident quantization, while the last term is used to encourage the network to have diverse quantization. The last part of the objective function is used to encourage the network to identify drivers that are spatio-temporally correlated with the impacts of extremes. E hat T here is the union of extremes at all time steps before the event, for example up to 7-8 weeks before the event. We invert this mask and we apply it on the valid regions. In other words, we want the network to identify non-drivers on this region. This is also helpful to unify the quantization code of the normal data. While we have ground truth data for the impacts of extreme, for example from remote sensing, we don't have any ground truth data for their drivers in real-world signals. To solve this issue, we introduce a new framework to generate synthetic data. For example, to generate a synthetic signal of a climate variable, we consider its typical value at specific time and location, for example, the mean value. And then we artificially predefine coupling between these variables and the impacts of extremes. And based on this coupling, we induce anomalies in the data. And this would be our target anomalies. In addition, we add some random anomalies in the data. And the task is to design a model that's capable to identify only the anomalies that are correlated with the impacts of extremes. Here we show qualitative results on one of the synthetic data. Shown are the input climate variable along with some random anomalies. Below are the target anomalies along with the prediction by our model. As can be seen, our model can correctly identify the relations between the variables and the impacts of extremes. We generate different versions of the synthetic data and we compare to several baselines. Here is shown the F1 score on one of the test sets. We compare, for example, to interpretable forecasting baselines such as integrated gradient, and to one class unsupervised anomaly detection, reconstruction-based anomaly detection, and multiple instance learning. As can be seen, our model outperforms all baselines. Now we move to real-world data, where we evaluate our method on two long-term real-world reanalysis data, Aero5 land and Sarah. We conducted our experiments on different cortex domains. Here is shown qualitative results on real-world data. On the top left is the extreme drought as reported from remote sensing, and on the right is the prediction by our model. Below is the temporal evolution of the identified drivers up to 7 weeks before the event, for example for soil moisture and for total evaporation. More details and results are available on our website. Thanks for watching.